Have you ever looked up and just watched a massive airliner climbing into the sky and wondered, how is that possible? What is that thing actually made of? Well, today, we're going to pull back the curtain on the invisible strength of modern aircraft and really dig into the incredible metals that make flight possible. Okay, let's get into it. So, to kick things off, here's a simple question. We all know steel is incredibly strong, right? We build skyscrapers, bridges, all sorts of massive things out of it. So why not airplanes? And the answer, well, it gets right to the very core of the biggest challenge in all of aerospace engineering.
And that challenge is what you could call the aviator's dilemma. To get a massive machine off the ground and keep it there, you are in a constant battle. You need materials that are unbelievably strong to handle all the forces of flight. But at the same time, they have to be incredibly lightweight. Strength alone is useless if you can't beat gravity. It is all about the strength-to-weight ratio.
So, where did engineers find the solution? They found it in this amazing family of materials, non-ferrous metals. Now, the name just means they don't have iron in them, so steel is out. But what's crucial is that they hit this perfect trifecta for aviation. They're strong, they're light, and they are way more resistant to corrosion than steel.
And when we talk about non-ferrous metals in aviation, there is one that stands head and shoulders above the rest. So let's meet the lightweight champion, the absolute workhorse of the entire aerospace industry, aluminum.
So what makes aluminum the king? It's not just one thing. It's this awesome combination of properties. First and foremost, it's got that killer strength-to-weight ratio. It's also super malleable and ductile, which basically means you can bend it, stretch it, and shape it into complex things like a wing's skin without it breaking. It naturally fights off corrosion. It melts at a pretty low temperature, which makes it easier to work with. And as a bonus, it's not magnetic and conducts electricity really well.
But hold on, not all aluminum is created equal. It's basically broken down into two main classes. You have casting alloys, where you literally just pour molten aluminum into a mold. That's perfect for really intricate, complex shapes, but the vast majority of an aircraft structure is made from wrought alloys. This stuff is mechanically worked, it's rolled flat, it's forged, it's squeezed into shape to create all the critical components like the fuselage skin, the internal stringers that act like a skeleton, and yep, thousands upon thousands of rivets.
This brings up a really fascinating point. With all these different aluminum alloys to choose from, how does an engineer specify the exact one they need for a part? Well, they use what looks like a kind of secret code, a designation just like this one, 7075-T6. It might look like a random part number, but it's not. It's actually a complete recipe.
All right, let's crack this code together. That first digit, the 7, tells you the main alloying element added to the aluminum is zinc, which is known for creating super high-strength alloys. The 0 right after it just means it's the original recipe, no special tweaks. The 75 part identifies this specific, unique alloy inside that 7000 series group. And finally, you get to the T6. This is the temper, and it might be the most important part. It tells you exactly how the metal was cooked. It's been solution heat treated and then artificially aged to bring it to its absolute maximum strength. So in that one short code, an engineer knows the metal's entire life story.
Of course, you can't build an entire airplane out of just aluminum. No way. For those jobs that require truly extreme performance, engineers have to call in the specialists. Let's take a look at what other metals are needed to get the job done.
So think of it like a team. Aluminum is the star player, handling the bulk of the work, the skin, the wings, the internal structure. But then you bring in titanium for spots that need incredible strength and have to handle extreme heat. We're talking about the firewalls that separate the hot engines from the rest of the plane, engine shrouds, and critical fasteners. And then there's magnesium. Its superpower? It is the lightest structural metal in the world. So you use it in places where saving every single ounce is the top priority, like in gearbox housings or seat frames.
And we've got to give a shout out to a few other key players. You've got copper, which is absolutely essential for all the wiring because of its amazing electrical conductivity. There's a special alloy called beryllium copper, used for precision parts like bearings that need to resist wear and fatigue. And then there's Monel, a tough nickel alloy that's perfect for rugged jobs like exhaust manifolds that have to be strong and stand up to corrosive gases. Okay, so we've got our list of metals. But a block of aluminum is a long way from being a wing.
So how do you turn these raw materials into precisely engineered aircraft parts? Well, that brings us to the processes of forging and forming.
At a high level, there are two main ways to work a piece of metal into shape. Hot working, as you can guess, is done at really high temperatures. This makes the metal easier to shape, and it actually improves its internal structure, making it stronger. The only drawback is you get a pretty rough surface finish. The other option is cold working, which is done at room temperature. This gives you a much nicer surface finish and increases the metal's hardness, but the trade-off is it makes it a bit more brutal. It's always a choice engineers have to make for each specific part.
For parts that are cast, the methods really range in their precision. You've got sand casting, the classic method where you just pour molten metal into a sand mold and let gravity do the work. For a bit more accuracy and a better finish, you can use a reusable permanent mold. But for the most complex parts, where every millimeter matters, you need die casting. This is where you force the molten metal into a steel die under enormous pressure. You can see the progression from simple to highly precise engineering.
After a part is shaped, there's often one final, absolutely vital step: heat treatment. This is like the final baking process for the metal. Remember that T6 from our aluminum code? That's what this is all about. It's a specific recipe of heating and cooling. In this case, a solution heat treatment followed by artificial aging. This is how you unlock the material's absolute maximum design strength.
So now you have your perfect part. It's made from the right stuff, it's been formed the right way, and it's been heat treated for maximum strength. But how do you really, truly know that it's safe to fly? Answering that question, well, it takes us to the most critical phase of all, the ultimate stress test.
90%. Just look at that number for a second. Let it hang there. 90% of what?
It refers to this: fatigue failures. It's when a metal part breaks under repetitive stress, over and over again, even when that stress is way below the metal's maximum strength. The classic example is bending a paperclip back and forth. It doesn't break on the first bend, but if you keep doing it, it will eventually snap. Now, imagine a wing flexing with every bit of turbulence on every single flight. Preventing fatigue failure is everything.
To guarantee safety, these materials go through an absolute gauntlet of destructive tests. There's hardness testing, which checks to see if the heat treatment worked correctly. There's tensile testing, where they literally pull a sample of the metal apart to find its ultimate breaking point. They do impact testing to measure its toughness against a sudden shock. And, most importantly, they do fatigue testing, putting a part on a rig and bending it, shaking it, and stressing it for thousands, sometimes millions of cycles to find out exactly how long it will last.
So from aluminum and titanium to the complex codes and brutal tests that prove their strength, these non-ferrous metals are really the unsung heroes of aviation. But you know, technology never, ever stands still. We are already seeing the rise of carbon fiber composites and other amazing advanced materials. So, the final question I want to leave you with is this: what material will define the next 100 years of flight? Thanks for watching.